Okay, we're in section 28. This is optimization and modeling. I'll certainly go through the lecture portion. After we do the lecture portion, which will include an example, we will go through more examples, and those examples will be done at the whiteboard as well. All right, we'll do that. And then hopefully you study that material, and then you decide that you can do it on your own by trying homework on your own. All right, and you try that. Again, if you need assistance, please feel free to come by during office hours, and I'll be more than happy to help you. All right. Right now, I want to switch to the whiteboard, and I'm hoping that as we present this to you, that you have a piece of paper and pencil out, and you're willing to think about what we're doing here. So let me go to the whiteboard, do another share with you. Just give me a moment here. And what do you have here? You have optimization problems. So what I want to do is just, again, I always say, read, and it's awful to be read too. But I realize a lot of times what it really is necessary that you read things. All right. And there's nothing wrong with that. But I want to point out, I'll just give you a little story here. I was once on a negotiation team, and there's two sides of the negotiation team, one side, other side. And this was about employment. All right, about a union employment. And what happened was I noticed the lawyers showing up, and what the lawyers would do, they would spend hours reading documents to us. Right. And I thought to myself, why are they doing that? And then I thought to myself, it was not the one lawyer, it was one lawyer reading and maybe 4 or 5 lawyers sitting at the table. So I was thinking about this. I said, computationally, this is a very expensive thing they're doing. And then I thought to myself, someone is getting paid to do that, to read to me. All right. Now, of course, it's, it's almost like a dance you're going through, and, the lawyers want to get paid. You have to sit through their nonsense, yada, yada, yada. It's really chaos. But anyway, let me read to you. We're back doing word problems again. All right. What's we're doing? We're doing word problems again. We're back doing word problems. What's a word problem? There's going to be words in it. I got to understand the words. So we're going to be using calculus to solve these problems. Now, typically, you have to realize what we're really trying to do after all the work we've done. We're trying to do some maximizations or minimizations of something. I don't know yet. We have to read it and find out what they're talking about. So I'm going to go, what I would like you to do is, I can't say it enough, we would love for you to read, right? Try to understand the story. Let me go back to those lawyers. When they were reading that stuff, I'll be honest with you, I don't think I really understood what they were talking about, because I really wasn't interested. I had much more basic interests involved. All right. I really wasn't interested in all their minutiae. I was really interested in what's the bottom line. Right. But there's other details I wasn't quite getting in the story. Their story was long, though. These stories would be very short. Here's the deal, though. You may need to read the story more than once. You may need to have someone read the story to you more than once. But these are going to be really simple stories. You got to focus in on their stories. Typically, in these stories, there will be a variable. Try to identify what the variable is in the problem. All right, there's some unknown. Right? They're usually trying to maximize or minimize this thing, right? Typically as a function, right? There's some variable and it's related to something by function. They're generally trying to minimize or maximize a function of a variable. I'm also going to claim that drawing a picture may be helpful. It may make it even worse, though, but I think pictures really do help, right? Bottom line, what are you doing? You're looking for a variable. I'm sorry, a function of a variable that you're going to try to optimize. What does that mean? Take a minimum or a maximum. Typically, it may not be a good idea to skip this. You want to know the domain of these functions. It should be clear. All right. What are you going to do? We're talking about calculus. So it's probably going to end up to be some kind of differentiation somewhere. Why is that? We use derivatives for optimizations, mins and maxes, and we'll go through examples. So let's do the first example. Not going to be too bad. It says find the point in the parabola x squared. How many points are on the parabola x squared? An infinite number of them. They want me to find a point in general. By the way, I'm going to take their picture. I'm going to say the point's over here somewhere. So what's the point going to be? The point's going to be x. They said find a point, right? What's the y coordinate? It's actually x squared. This is the variable in the problem, by the way, x is. If I know what x is, I will certainly know where the point is. But then they said they want to make it as close as possible to the 0.30. This is the 0.30. When you read that, you should realize what they're trying to do is minimize the distance between those 2 points. Okay, here comes a problem for a lot of students. They're looking at this and wondering, what's the function? It's a Math 100 function. I'll write that down for you. So distance is going to be equal to, so you learned in Math 100. You did it by the Pythagorean theorem. Let's write this down. X squared minus 0, that's the change in y's, plus x minus 3, that's the change in x's. I want to minimize this, and this distance is a function of x and x alone now. We want to minimize. How do I do that? Well, one thing, I'll be honest with you, it would be nice to know the domain of the problem. All right, I got to tell you something. Just looking at the picture, x could be any real number. But, kind of looking at it, and I want to point what I mean I'm looking at. I'm kind of looking at it over here. And, certainly someone says, it could be any real number, but I'm going to say, I think it's probably over here somewhere. Right, that looks like the smallest is, because if I went over here, it looks like it's getting larger and larger. So what I'm going to say over here, just kind of looking at the picture, I'm going to say probably it's certainly reasonable to say, hey, x is probably greater than 0. All right, go back over that again. If I'm looking at this picture, which is accurately drawn, and I'm trying to minimize the distance, I'm going to say the minimal distance appear to be somewhere here about. I'm going to say the x is definitely better than 0. By the way, over here, it's just way too far, right? You get the idea, way too far away. So what do I need to do? I need to look at this function now and minimize it. How do I do that? I take its derivative. Before I do that, though, I want to claim it may be a good idea to simplify this. I'm going to write this down a little simpler, but not a lot simpler. You're going to get x4 plus, stop me if I go too fast, x squared minus 6x plus 9. All right. I did okay, right? X squared, yeah. Let me keep writing it. This is the root of x4 plus x squared minus 6x plus 9. I got to take its derivative now, right? What's that going to be? 2 root. I'm getting better at doing square roots now, right? By the way, that's distance. That's what this thing is. This is distance. I hope you can agree that D is never going to be 0, looking at that picture. I don't have to worry about division by 0, by the way. D is always a positive number. What goes on top? The derivative of the inside, which is going to be 4x cubed plus 2x minus 6. Well, you know what I'm going to do? I'm going to divide through by 2 now. I may be delaying the inevitable, but that's okay. What do you get over there? 2x cubed plus x minus 3. Now, what do I have to do? This is the derivative. I have to analyze this derivative number line above 0, and this is the derivative. What am I looking for? Critical points. Here's my problem. I'm looking for a critical point, and I got to look at this thing over here And the only critical point would be when this thing here becomes 0. Well, here's the deal. I'm looking at it and I'm wondering, did I learn anything in Math 119 that would allow me to do that? And what you learned in Math 119 was the rational root theorem. All right. You know what? I think I really hacked the theorem word up there. All right, theorem. What do? I'm going to take the easiest one possible, but I've asked with you, I think I could look at the picture, help me with it. And look at the picture. I'm going to say maybe 1 might work. 2 plus 1 minus 3 equals 0. I found the critical number. What's that going to be? 1. All right, let's take a look. And I'm going to take a test point. What's a good test point after 1? I would say maybe like 2. If you plug in 2, what would you get? You definitely get a positive number. What does that mean? That means f is increasing. Now let's take a number below 1, like a half, and plug it in. And what would you get? I'll do that for you. By the way, we're plugging it in here. I'm not worried about anything else. Plug in a half, you get 4 times an eighth, which is a half. Again, the test point we're using is a half. 1/2 cubed is 1/8. 4 times an eighth is 1/2. Now plus 1 minus 6, clearly negative. What have we found? A minimum. We found a minimum. So the minimum occurs at the point 1. What's the y coordinate going to be? It's x squared. It's going to be 1. Let's go back to the picture. And you know what? Looking at it, the picture's not bad. That's the shortest distance right over there. What's the shortest distance? At the point 1, 1. All right. So I'm going to claim over here, you know, I certainly wrote it down for you. We talked through it. Certainly there's a lot written over there. I realize that. We draw a picture down of the final thing. I do want to point out for those students that have taken geometry, what do we know about this one over here? We're looking at it. It's going to be perpendicular to the tangent line over there. I guess I could have figured that one out too, by the way, going back to some simple geometry concepts over here. But what's the point of minimal distance? 1, 1. All right. So I realize for a lot of students, that's a lot of work. And someone says, oh, you wrote a lot of stuff down for that. You're right, I did. I wrote a lot of things down over there. But for the most part, you know, pretty simple to do. I don't think I divided 3 by 2, but you could do that. I did that before. What do we need to do, though? We just gave one example, but here's the problem. Let's go back to the first page. Here's what we're looking to do. Read, draw a picture, know the variable, know the function of the variable that we're trying to do something, either minimize or maximize, and use calculus to figure it out. What's calculus going to do? That first derivative, mins and maxes. That's what we're trying to do. What's an optimization problem? Mins and maxes. Thank you.